Good morning, students. In today's class, we'll start our topic of first midterm revision. In first midterm revision, we'll start with the Miller indices. So, in the important questions for the first internal will be in the examination. There is a possibility of asking what are Miller indices and how are they obtained. So, the Miller indices are, as you know, that we have started with the unit 1. So in that, it is a notation of planes, right? So what is that planes? I'll just show you. So planes are nothing but the line segments, which are what you can say. The planes is this is what we have done. Okay, see, right? Now these are the imaginary points, right? Okay, everybody. So these imaginary points, when they are drawn, right? See these imaginary points, you can just see this is the imaginary points, and these imaginary points, when they are joined with the line segment, we'll just call that as planes, right? I'll just show you, right? So these line segments, when I just draw this, right, when you join these imaginary points, I just call this particular see, this is what planes, right? So this is called notation of planes. So these notation of planes, so further you can just see this, I'm talking about this. So when you just see this, these are the points. Now these are the points, right? So when I just drawing this, you can just see this is what H plane, and this is mathematically written as K, and this is written as N. So you can just see this, the notation of planes, right? In is nothing but these are known as the Miller indices, right? So now we just start with our today's topic of Miller indices. The examination, it will ask you what are Miller indices and how are they obtained. The question will be like this, right? So you can just make a note of it. See, what are Miller indices? The question will be like this. The question will be what are Miller indices? See, what are Miller indices and how these Miller indices can be obtained. Now, this will be the question, important question of the mid one examination. So, what are Miller indices and how are they obtained, right? So, we just see, deal with this today's topic with this. Okay. Now we just deal with this today's topic with the Miller indices. So what are Miller indices? Miller indices are nothing but the line segments which are joined with the imaginary points which have been joined with the line segments and which are represented mathematical by HKL. So planes, we just say these are planes, right? So we just say this is representation as the Miller indices, which has been discovered by the scientist Miller. We just say that Miller indices are the reciprocals of the fractional intercepts, which is formed when the planes are making the with the crystallographic axes. We just say that it's called Miller indices. Miller indices are the smallest possible integers. You can just say the Miller indices are smallest possible integers whose reciprocal has the same ratio as the planes, which is making the crystallographic axes along x comma y comma z, right? So now we just say this is called Miller indices. Now, so I will just explain that more clearly when you just see this in the next slide. So Miller indices are the reciprocals of the fractional intercepts which the plane makes with the crystallographic axes x comma y comma z axes of the three non-parallel edges of the cubic unit cell. Now, unit cell, you already have the information. Unit cell is nothing but a smallest geometrical figure which can be drawn in 3 dimensions. We just say that is called unit cell. Now, the orientation of the planes or the faces in a crystal can be described in terms of the intercepts of these 3 axes. See, the orientation of the how they look inside the crystals, right? See, these HKL planes is they are oriented in a particular direction. If they are oriented in horizontally or vertically or inclined and so on, that is explained by this term orientation. So the orientation of these HKL planes or faces in a crystal can be described in terms of their intercepts which are made on 3 axes. So Miller introduced a system. Miller is a scientist. I told you, Miller is a scientist which introduced a system to designate the plane in a crystal. Right? Miller introduced a system to designate a plane in a crystal. So he introduced three set of numbers which specify the plane in a crystal. Just now I have shown you. So now this set of three numbers is known as Miller indices. As you go move forward, you can see this, right? As you move forward, right, we'll just move to the next one. You can just see what is this set of three numbers, right? Now, so these are the, see, this is the orientation, different lattice planes which are present inside a crystal. You see, this is the imaginary points. I've joined this imaginary points with the line segment. You can see this. These imaginary points will be there in the inside the crystal. So you can just draw this line segment, right, in this particular fashion, in the vertical way, in the horizontal way, and this particular fashion. So the distance between any two consecutive planes nothing but that is called interplanar spacing, that is represented with d. Now this d is same as this d, and this d in a particular crystal system, right? So now, so what is the procedure to find this Miller indices, and what is the use of studying this Miller indices? So Miller indices are mathematical notations, smallest possible integers, which gives us the information of the uh, uh, more occupancy of the atoms, molecules, or we can just say that is called constituent particles, which are residing inside the crystal. That occupancy level will be explained, will be mathematically can be known by means of Miller indices. So by making use of this Miller indices, uh, one can know that the more number of constituent particles which are present in the given crystal mathematically can be known by means of this Miller indices. So I think that you got a clear idea regarding this Miller indices. So again, I'm repeating the same thing. The Miller indices are the smallest possible integers, which has the same ratio as the reciprocal, which is on the concerned plane along the three crystallographic axes, that is x comma y comma z. So so first of all, what is the procedure? Okay, just now we have just gone for some schematic diagram. Now what will be the procedure to find out this Miller indices? Let us see. First of all, you determine the coordinates of the intercepts made by the plane along three crystallographic axes. We have to determine the intercepts along the crystallographic axes and then express the intercepts as the multiples of the unit cell dimensions, or we just say that is called the lattice parameters, right, along the three axes, that is a comma b comma c. So express these intercepts as the multiples of the you can say the lattice parameters along the axis. So determine the reciprocals of these numbers. So then when you just determine the intercept, see what we are doing here is that first of all we are determining the coordinates of the intercepts made by the plane along the three crystallographic axes. Then what we are doing here is that we are just whatever the intercepts you got, we are just writing the reciprocals of that particular intercepts along the three crystallographic axes. Now, whatever the value you got, these reciprocals that can be converted or simplified into smallest whole number. So how you can convert the smallest whole number? By means of multiplying each of the reciprocal term with the LCM, right? So whatever the LCM you'll get, I will show you the example what actually we are doing. So when you just multiply this, what you can say the reciprocals with their LCMs, so we will get the smallest whole number, and we have to enclose whatever the term, whatever the simplified values, whatever we are getting, that should be enclosed with this particular graphic. Now this gives the Miller indices HKL of the plane. So now whatever the value I'm getting, right, I'm just representing this as HKL. So that simplified value is HKL. Whatever the value, whatever the numbers you get, that values are represented. Now we are just representing it or denoting with HKL of the plane. Now I will show you this one of the example. So let us we'll just take a cubic unit cell. This is a cubic unit cell, and I want to know the Miller indices of this plane. You can see A, B, C, D is one plane, right? A, B, C, D is one plane, right? So A, B, C as a is the dimensions A, B, C are the dimensions of the unit cell along x comma y comma z axis, and this is the plane, right? So this plane, we can just write this plane as, see, this is we just represent that as some A dash, Now this is what B dash, and this is only representation part. Now this is what C dash, and this is the plane I'm talking about. This is D dash. So we are talking about A dash, B dash, C dash, D dash plane. You can see I'm talking about this plane, right? Clear, everybody? So I want to locate the intercept of this plane. Clear? I want to locate the intercept of this plane. A dash, B dash, C dash, and D dash. So how will I will locate? So just see. See, I want to locate this, right? So what I'm doing, so I'm just writing, see, what is the dimensions or what is what the intercept you will get the on the x-axis? What is that intercept? Let us, we are just to write the dimensions of the unit cell along the x-axis. That is A. And here on the y-axis, what is the dimension where the plane is cutting? Let us consider that is B. And C, you can just see, it is not exactly cutting. So this C is parallel to z-axis. You can just see. I will show you. This C is parallel to, you can see this C is, the plane is not exactly cutting, but this is parallel to z-axis, right? This is exactly parallel to z-axis. You can see this is parallel to your z-axis, right? This is what we are talking about. This is the z-axis. So this is parallel to z-axis. So this C is parallel to z-axis. So any plane which is parallel to the z-axis, so that will be taken as infinity. So I've taken this as A dimension from 0 to A. What will be the length? Let us consider that length is 1. And from 0 to B, what is the length? Let us consider that is 1. And here, since this particular value is parallel to z-axis, I'm just taking it as infinity. So I'll show you that one, right? Clearer. Now I will just show that particular aspect, right? Within see, before going to that, see, if a plane is parallel to any of the coordinate axis, then its intercept will be infinite. We have just seen that particular diagram. By seeing the diagram, you can just see that this C is parallel. See, I'm talking about this. See, this C, when C is not exactly cutting the z-axis, because otherwise you can just see this A is cutting. This is the x-axis, and A. See, this x-axis has having a dimensions A. Here it is cutting, so I'm just writing it as 1. Here the B is there. So from here to here, we are just taking it as 1 unit. So here C, it is C. You can just see C is not exactly, this plane is not cutting it, but this plane is exactly parallel. You can just see this is parallel to z-axis, right? This is parallel to. So I've just now I've shown you the important features. If a plane is parallel to any of the coordinate axes, then its intercept should be taken as infinity. And what is the I will just come to that also. So one by one, so 1 1, so therefore the dimension, the distance is the 1. I've given you we have written 1, and B here it is 1, and C is parallel to the z-axis. Just that is the reason that we have written as infinity. So just reciprocal of it, 1 by 1, 1 by 1, and 1 by infinity. So we are reciprocaling it. We are writing that as the inverse of it. So 1 1 1 by infinity is 0. So when you take LCM also, the LCM of 1 is 1. So therefore, 1, therefore just take it as 1. We just multiplied it. So we got 1 1 0. So the Miller indices with this particular bracket of this particular plane is found to be 1 1 0. In the same way, we are having various examples. So we'll just take this example, right? One more example. See, let us consider this is the plane. You can just see from 0 to here, the unit is taken as half. See, this here the dimension is A here. So here when you just compare this particular distance, and this distance is exactly half of this distance. Therefore, we have taken the intercept as half. When you just move to the B, this is completely, we have taken it as 1. You can just see 1. Here, you can just see this distance is half, and this distance is 3 by 4, right? Because from origin to this particular mark, the distances we are considering it as 1. From origin to this mark, it is 1. From origin to this mark, it is 1. So whatever the term below that, you see here we are getting very, this particular part is near to origin. Therefore, we have written it as half. Here, this particular plane is exactly cutting at this particular mark. We are taking it as 1. And here it is nearly equal to 1. So the third part, 3 by 4, right? If we see, you can reduce this 1 by 4, 1 by 4, 1 by 4, 1 by 4. So 4 1 by 4 will give you, fetch you 1 value. So here 1 by 4, 1 by 4, and this is 3 by 4. Remaining is 1 by 4. 3 by 4 plus 1 by 4 will fetch you the 1 value. So I think that you got clear idea. So 1 by 2, 1, 3 by 4 we have written. Reciprocal of it, you will get 2, here 1, and this is 3, 4 by 3. So 2, 1, 4 by 3. So what is the LCM we have to take? 2 by 1. Here also 1. So 1 comma 3 LCM is how much? Definitely you'll get 3. So you just multiply this 3, whatever the value you got, I will show you. If you have not understood, see here we have what we have writing 2 by 1, right? Here 1 by 1. Clear? So we have taken the LCM. We have to take the LCM. LCM 1 comma 1 comma 3. See, this is the what we got 1 comma 1 comma 3. So what is the LCM of 1 1 comma 3? That is 3. Now what I'm doing is that whatever the value we got LCM, we are multiplying with this 3 here. So here, what is the value we got? What is the LCM we got? 3. So we are whatever the LCM you got, we are just multiplying it. Here also we just multiply with 3. Right? This is in the denominator. This will get, this will out. So this 3 ones are, see here. See, you can just say 3 ones are. Here 3, just have 2 into 3 is 6, right? So this will 2 by 1 into 3, that is 6. We'll get 6. So here you'll get 3 and 3 get cancelled. Only 1 is there, no? So just we'll get this. That as see, whatever the LCM you got, that is LCM is 3 you got, right? I'm just multiplying this 2 into 3. What will get 6? Here, what is LCM I got? 3. So I'm just multiplying it with 3. 1 into 3 is 3. Here I'm just multiplying with 3. The denominator t, numerator 3 will get cancelled. 4. So what is the Miller indices of this particular plane? 6, 3, 4. You can see this is the example of the Miller indices. So I think that you got a very clear idea regarding how to do this problems, right? Now I can just say different planes. Now, what is the important feature? The first one we have discussed. Now all the parallel equidistance plane have the same Miller indices. Miller indices define a set of equidistant parallel planes. Just now I have told you, when we see the diagram, they are equidistant, right? You can just see this is equidistant. We are talking about, see, they are equal. This particular plane is like equidistance. You can just see they are equidistance when compared with this neighboring one. So we are just discussing the same thing here. So you can see. So Miller indices define a set of equidistant parallel planes. If the Miller indices of two planes have the same ratio, then the planes are parallel to each other. So for example, you got the Miller indices in the form of ratio 4:2, 2:8, that can be equal to, see, if this is the what you got, 4:2, right, 2:8. So what this particular value say? If the Miller indices of two planes have the same ratio, then the planes are parallel to each other. Definitely. This is 2, this is 1, and this is 4. Let us see. 2:2, 1:4. So this 4, 4, 4:2:8 is same as 2:1:4. This is a what meaning this particular statement will tell us. If the Miller indices of two planes have the same ratio, then the planes are parallel to each other. If HKL are the Miller indices of a plane, then the plane cuts the axis into HKL equal parts. See, just now we have seen with that. Now, see, unless you, I think that you got at least a very good idea regarding how to determine the Miller indices. See, if any plane is parallel to any axis, then it is taken as infinity. And if the plane, you will get negative one also. So for example, you get a negative value of the Miller indices. For example, you got the intercept as -2. For example, you got the intercept as -2. This can be written at last with the Miller indices. See, whatever the value you'll get, you have to write with 2 bar. If the intercept of the given plane is negative, then that Miller indices of that particular intercept can be written as with 2 bar. So whatever the value you will get after the simplification, you have to just represent that with the bar. Clear, everybody? So that aspect that you have to remember. So as you move on to the next one, this is about the Miller indices. Now, see the interplanar spacing. So what is the interplanar? The distance between the planes define the same set of Miller indices, and it is same with different crystal system. For cubic crystal system, the Miller indices formula, general formula of Miller indices given by this particular 1 by d square is equal to h square plus k square plus l square by a square. You can just see the video how we have determined the Miller indices of the cubic crystal. And if the crystal is tetragonal, this is the interplanar spacing formula, and how this is the case for orthorhombic and so on. Now, this is what we have planned for today's class. So now these are the few, you can just see this is the problems of the Miller indices of, you can be, except by using the xray diffraction method. I'll just show you. Give the ratio of interplanar distances of 1, 0, 0, 1, 1, 0, 1, 1 plane for simple cubic structure. For simple cubic structure, you know that this is the basic formula. D is equal to A by, this is what the cubic crystal system is, we have to write h square plus k square, right, plus L square whole to the power of 1 by 2. Now, see HKL, what is HKL? You can just see, we are talking about HKL. So what is HKL? This HKL is nothing but, we can just see the from the figure, HKL is 1, 0, and 0. This is the values what you have to get. HKL is 1, 0, 0. So the distance, you can just measure it very easily. A will be same for cubic crystal system. HKL will be changing. So HK instead of HKL for, I'm talking about this one, right? You can, for this one, the H is 1, K is 1, and L is 0. In the same case, in the next one, H is 1, K is 1, and L is 1. So you have to just substitute these values, and whatever the value you got, you have to write with the A. So if they are asking for the ratio, then A will go, and whatever the simplified version you'll get, now that will be your exact value of the ratio of interplanar distances. So right now with this, we just, I think that you had information regarding this. When we just move forward, right? So we started with this. See, we started with Miller indices and what is interplanar spacing and how, what are the different interplanar spacing for cubic crystal system, tetragonal, orthorhombic, and so on. So we, with a very clear idea, we just move forward. What is actually the meaning of diffraction, and what is diffraction in crystal, and X-ray diffraction in crystal. Diffraction, you had the information, right? Whatever the light ray, when light ray is traveling inside the crystal, so at the orifice or the end faces, at the end surfaces, again the light ray will reflect back. So we'll just say that's called whatever the image or whatever the geometrical shadow of the object, right? Whatever that particular geometrical shadow of the object. So we just say that the bending nature of the light at the end faces or the ends of the object, which is that is called the diffraction in light. So now this particular aspect, main important condition for diffraction is, see, the slit should be in the whatever the opening is there, that opening, or we just say that is slit in our language of physics. So it should be in the order of incident light wavelength, right? Diffraction crystal has been first discovered by Loy. So Loy is the scientist who has given us the information, right? Diffraction of light in a crystal and X-ray diffraction in crystal has been given by Friedrich and Knipping. Now, this is what we will use for different applications, right? Why we should study? I've just shown you the different with the different applications, right? Due to the X-ray crystallography, you get a very good image of your thumb, the fingerprints, and you can just see this. This is the structure of your bone, and this is what you, when you go to the airport security, and this you can just say that is called the image. Your what you can say, the image of your thumb or finger. So right, the production of X-ray, you had a very good information. Bragg's law equation 2D sin theta is equal to n lambda. With this condition only, diffraction is occurs, right? So we are moving to towards the powder method, right? What actually we are interested in the. So So when we will just move to the powder method, we can see the crystal has been what are the crystal what are the crystal form? That crystal form is taken in a polycrystalline. That should be polycrystalline crystal. Instead of single crystal, we just use a fine powdered crystal, and particularly we talk about the polycrystalline crystal. And here we just we remember that we are taking the monochromatic. Monochromatic is single colored X-ray. So now diffraction, you will get a diffraction of the plane wave with these particular conditions should be satisfied. That is, it should obey the Bragg's equation, that is 2d sine theta is equal to 10 lambda. So the camera that we are using, that is DB Shearer, which has been discovered by these two scientists with a DB Shearer camera. So a small amount of powdered material is sealed in a capillary tube, a fine capillary tube, which is made up of glass, and that does not actually diffract the X-rays. This sample is placed in a DB Shearer camera, and it is accurate aligned at the center of the camera. So the powder will be diffracted. As I say, the powder will be diffract the X-rays in accordance with the Bragg's law to produce the diffraction beam. So whenever the when we just take out these cones, we'll get a different cones with the X-rays as it is entering. So when it is incidenting, you can see when the X-rays are incidenting at the this particular right capillary tube, when it is going inside, you'll get a reflection, back reflection, and the forward direction there is some deflection that will be impinged on this negative film, and you'll get this type of image, right? So when the film is removed from the camera and then show the diffraction lines as it is showing here, so you can guess for several random orientation of the crystal, you can just see that this is a diffraction. In the case of powdered sample, diffracted beam will form a continuous cone. So just now I've shown you these are the types of cones, right? And now you can just see this is the when you just take out this particular step, when mathematics is applied to that, so you'll get a value of 4 theta is equal to s by r, and theta is equal to 1 by 4 pi s by r. That is when we convert from radians to degrees. So we'll get the value of the what you can say at different angles. We'll get a different values at particular angle. We'll get a clear picture of that particular cone, right? So cone of these, you will get a structure of exact structure of this particular angle that we can calculate by means of this formula. Okay, so we just studied some experiment, right? Whatever the experiment you studied, so what is the application of that one, right? This X-ray diffraction technique is used to know the difference between crystalline amorphous material. We just explained you regarding this crystalline amorphous, and you can know that structure of the crystalline material and how this orientation is there inside the crystal, and how this strain and small grain size which we use for different applications. So here the X-ray diffractions are used for different many advantages are there. Most conveniently will method to determine this exact structure of the crystal can be determined by using this X-rays. X-ray XRD you already have it for different research purpose. You just go for X-ray diffraction. XRD refers to X-ray diffraction. If you want to know the minute information, right, of that particular right crystal, so you just we are talking about crystal, right? So that is the reason that I'm telling you that we are talking about X-ray crystal, right? So XRD of the crystal. So by that reason, you can just have different materials, whatever the material information you got, that minute information you'll get by means of this X-ray diffraction, right? So yeah, the X-rays are why X-rays are preferred. X-rays are not absorbed very much by air, so the sample need not be in an evacuated chamber. You need us. This is very important one. See, everything whatever we'll just keep in the experiment, that should be an evacuated chamber. That is not the case for this X-rays. So here only one disadvantage for X by using X-rays, it doesn't interact strongly with the lighter elements, right? So very strongly they will not interact, but we'll get an information, right? Whatever required information we'll get. So that particular part we'll get. So in today's topic, we just discussed two long answers which are very important for us. So the first one is regarding the Miller indices. What are Miller indices and how are they obtained? What are powder method? Explain the powder X-ray diffraction powder method, right, by DB Shearer method, and what are the applications of the X-ray diffraction. Just now we have gone through that. So with this, I will just take an end. So today's class, we'll end today's class. Thank you everyone. Thank you for your patience. So again, if you have any doubt, you can just WhatsApp me regarding the other doubts, right? Please do that as early as possible. Thank you everyone.